Chapter 10, Part 2, Reactions of Alkanes. This part of the chapter is going to be really interesting because up until now, we've mostly talked about alkanes as being inert. The only reaction that you know of so far is that you can actually burn an alkane. That process is called combustion. This is going to be the first time that we see reactions that actually affect the functional groups of alkanes and add functional groups to alkanes. This is the only place in organic chemistry where we see this. So let's look at the reactions of alkanes with halogens. So you can take an alkane, which we've shorthanded using RH, react it with a halogen, and end up with an alkyl halide and an equivalent of halogen acid. This only works with fluorine, chlorine, and bromine. So there is kind of a problem with this reaction, and it's that once it starts, it has a really difficult time stopping. And so you end up with a pretty big mixture of products. So for example, if you were to run this reaction with methane and chlorine, you add heat or light to initiate the reaction. The heat or light will cause the chlorine molecule to break up into two equivalents of chlorine radical, which will then propagate the reaction further. You end up with a mixture of mono, di, tri, and tetra substituted products, as well as your hydrochloric acid, which is easy enough to deal with. Let's talk about the mechanism so we can see how this happens, and then we'll talk about ways that we can control this reaction and the different levels of reactivity of different halogens. So we're going to take a look at the reaction of methane with chlorine in the presence of light, and we're only going to look at the formation of chloromethane. From there, you can actually extract and or extrapolate, I guess, and see how the rest of the products are formed because the process is identical. But we don't want to be here drawing mechanisms forever, so we're only going to look at one. So in the first step, which is initiation, the radical, the halogen molecule is going to break apart to form two equivalents of radical. So this first step is called initiation because we are creating the radicals and initiating the reaction. The next step is propagation. This involves the radical and the alkane. So in this step, we have a couple things happening. The radical is going to try to form a bond with one of the halogen atoms. This is called extraction. You say that the chlorine radical is extracting a hydrogen atom from the alkane. And the way that it does this is actually by kind of meeting it halfway. And so what we just said by drawing these arrows, let me switch colors, is that this electron and this electron are going to come together to create a bond between the chlorine and the hydrogen. So that's what those arrows say. And then since we're breaking the bond between carbon and hydrogen, we also have to take the other electron and put it onto the carbon atom. So what this does for us is it creates a molecule of hydrochloric acid, and I'm going to draw it in the Lewis dot form. Instead of drawing a bond here, you can see that there are two electrons involved in that bond. And then we also have our methyl radical. So in the next step, which is also a type of propagation, the methyl radical that was formed can react with a molecule of chlorine, and it's going to do kind of the same thing. The electron from the alkyl radical is going to go here. It's going to pick up an electron from between the two chlorines, and then the other chlorine atom is going to leave. Oops, that arrow didn't come out. That other chlorine atom is going to leave with an unpaired electron. So now what we have is a molecule of chloromethane. The two electrons from the radical on the methyl group and from between the two chlorine atoms ends up in the covalent bond. And we also have a chlorine radical. Oops. So notice the important thing about propagation steps is that a propagation step always creates a new radical. So in the first propagation step that was listed, we created the methyl radical. In this new propagation step that we looked at, we created a chlorine radical. And this is important because it's like a domino effect. It keeps the reaction going. If you don't create a radical, it's a termination step, which is how the reaction ends. So at some point, all of the radicals will have reacted, whether they are forming multi-substituted alkanes or forming a halogen acid. Eventually, they all will be terminated. And so one example of this is the methyl radical reacting with the chlorine radical to create a molecule of chloromethane. Now notice this has the exact same outcome as the propagation step that we saw above, right? We're still able to make chloromethane through either propagation or termination. The difference here between these two steps is that the propagation reactions always ended with one radical. The termination step takes two radicals and ends with 0 radicals. So one radical in the starting material for propagation, one radical in the end. In an initiation reaction, you start off with 0 radicals and you end with 2. In a termination reaction, you start with 2 radicals and you end with 0. So let's summarize this mechanism again, in words this time. So in the initiation step, we have the homolysis of chlorine, and chlorine radical is formed, 2 equivalents of it. We have 2 types of propagations here. We can have a hydrogen atom abstraction, where hydrochloric acid and the alkyl radical are formed. We can also have a halogen atom abstraction, where the covalent bond is formed between the alkyl radical and the chlorine atom, and another chlorine radical is formed. And then we also have termination reactions, where the alkyl radical and chlorine radical form a covalent bond, and the radicals are consumed. Radical reactions, again, are a chain reaction. Each step generates the reactive intermediate that is required to initiate the next cycle of the reaction. And if you kill off all the radicals, that is considered a termination step, and it does end the reaction. So let's take a look at the reactivity and selectivity of chlorine. Chlorine is typically unselective. It is a highly reactive halogen as far as radical reactions go. It does not discriminate between primary, secondary, and tertiary hydrogen atoms when it is attempting to make a radical. It will happily abstract a hydrogen atom from any of these carbons. So for example, if you react chlorine with 2-methylpropane, we have 2 different sources of hydrogen, and chlorine is happy to abstract either and create a whole mess of products. Notice that, like, due to the fact that there are so many more of the methyl groups, even though the the primary radical that would be formed on the methyl groups would be less stable, it forms pretty readily because of how many of them there are. When you compare the fact that there are 9 methyl hydrogens to just the 1 methine hydrogen in the middle, it shows you how much more stable that tertiary radical must be if this much of the tertiary product is formed. And then you also end up with a good number of polychlorinated products. Now, if you take away that center carbon and use a quaternary compound with these 4 identical methyl groups all the way around it, there's only going to be 1 possible monosubstituted product. You will still have possibly quite a few polychlorinated products as well, but only 1 possible monosubstitution product. And notice up here we had 2 different monosubstitution products. Now, bromine is a lot more selective and therefore less reactive. Sorry, that was my cat. Reactions with bromine will typically go through the more stable / more easily formed radical. Those are one and the same typically. Also, bromine is, since it's less reactive, it requires both heat and light to initiate the radical reaction. So in the same reaction that we saw on the previous page with chlorine, we ended up with a mixture of 2 different monochlorinated products. But if you do the same reaction with bromine, first of all, you need light and heat, not or. And you're only going to get the product that is formed through the more stable radical. Whereas in the other reaction with chlorine, the less substituted chlorine product was more common. And you still got a good amount of this though. Notice I'm also not indicating the presence of any polybrominated products, and that's because you don't really get any. You tend to just get the one product that was formed through the more stable radical.